Chapter 5 Chapter 5 Ethereum Clients. An Ethereum client is a software program that implements the specification for Ethereum and interacts with other Ethereum clients via the peer-to-peer network. Different Ethereum clients communicate if the reference specification and structured communications protocols are met. Although these different clients are handled by various teams, they all sing the same protocol and obey the same rules in different programming languages. Mostly, they can all be used to run the same Ethereum network and communicate with it. Ethereum is an exposed source task, and the source code for all major clients is available for free download and use under open source licenses, e.g. LGPL version 3 for any reason. However, open source does not mean more than just free to use. This also means Ethereum is being created by an open volunteer group and can be updated by anyone. More eyes means more accurate code. Ethereum is defined by a standardized specification called the yellow paper. It compares with, for instance, Bitcoin, which is not formally defined, where the specification of Bitcoin is the Bitcoin Core Reference implementation. The specification of Ethereum is described in a paper incorporating an English specification with a mathematical one. In addition to numerous Ethereum improvement protocols, this formal specification specifies an Ethereum client's basic behavior. The yellow paper is revised regularly as major improvements are being made to Ethereum. Thanks to the simple formal specification of Ethereum, an Ethereum client has a range of independently produced but intolerable software implementations. Ethereum has a greater diversity of network-run implementations than any other blockchain, which is widely considered a positive thing. Indeed, it has proved to be an effective way to protect against attacks on the network, for example, as modifying the development technique of a specific customer actually hurts developers when patching the vulnerability, while other customers keep the network running almost unchanged. Ethereum Networks. A number of Ethereum-based networks exist that are largely in compliance with the formal specification specified in the Ethereum yellow paper, but may or may not communicate with each other. Ethereum, Ethereum Classic, Musiccoin, Ubiq, Expanse, Ella, and more than a few are among those Ethereum-based networks. While often protocol-level compatible, these networks also have features or attributes that allow Ethereum client software maintainers to make minor adjustments to suit each network. But not every version of Ethereum client software runs any blockchain based on Ethereum. There are currently 6 major implementations of the Ethereum protocol, written in 6 different languages. Parity, written in Rust-Geth. GoCPP Ethereum, written in C++. Pytherium, written in Python. Mantis, written in Scala. Harmony, written in Java. In this section, we'll look at the 2 most popular clients, Parity and Geth. We will show you how a node can be set up using each device and explore some of their command line choices and programming interfaces, APIs, for application. Will I have to run a complete node? The resistance of blockchains to well-being, durability, and censorship depends on them having multiple complete nodes running independently and distributed geographically. Complete Node will support other new nodes to get the block data to bootstrap their operation and provide an authoritative and independent check of all transactions and contracts to the operator. Yet operating a complete node would incur a cost of hardware resources and bandwidth. A full node will download 80 through 100 gigabytes of data as of September 2018, depending on the configuration of the client, and store it on a local hard disk. As new transactions and blocks are introduced, This data burden increases very quickly every day. For the creation of Ethereum, a complete node running on a live mainnet network is not needed. You can do just about whatever you're willing to do with a testnet node, which links you to one of the smaller blockchains in the public test, a local private blockchain like Ganesh, or a cloud-based Ethereum client provided by a service provider like Infura. You've also got the option to run a remote client that doesn't store a local blockchain copy or verify blocks and transactions. Such customers deliver a wallet's features and can build and broadcast transactions. Virtual clients can be used to connect to existing networks, such as your own complete node, a public blockchain, a testnet, or a private local blockchain. For practice, a remote client such as Metamask, Emerald Wallet, Myetherwallet, or MyCrypto is likely to be used as a fast way to switch between all the numerous node choices. The words remote client and wallet are used interchangeably, although some variations do exist. In addition to a wallet's transaction capabilities, a remote client usually provides an API, such as the Web3.js API. Don't confuse the idea of an Ethereum remote wallet with that of a light client, analogous to a Bitcoin simplified payment verification client. Light clients authorize block headers and make use of Merkle proofs to verify and evaluate their impact on the inclusion of transactions in the blockchain, giving them a comparable degree of protection to a full node. In comparison, customers remote from Ethereum would not check block headers or transactions. They completely trust a complete client to give them access to the blockchain, and thus lack significant assurances of protection and anonymity. When using a complete client you run yourself, you can minimize those problems. Full node advantages and disadvantages. Operating to run a complete node will help with the operation of the networks to which you are linking, but will also incur some mild to moderate costs. Let's dig at some of the benefits and the inconveniences. Advantages. Supports Ethereum-based networks stability and censorship resistance. Authoritative confirmation of all transactions. Can communicate with any public blockchain system without any intermediary. Can directly inject contracts into the public blockchain without any intermediary. Can offline check, read only, the blockchain status, accounts, contracts, etc. And question blockchain without letting a third party know the information you're reading. Disadvantages. Require substantial hardware and bandwidth resources. It can take several days to completely synchronize when initially started. Must be managed, updated, and kept online to keep synchronized. Public testnet advantages and disadvantages. Whether or not you wish to run a complete node, you will probably want to run a public test node. Taking a glance at some of the pros and cons of using a public test node. A test node has to synchronize and store much fewer data, about 10 gigabytes depending on the network, as of April 2018. A testnet node will completely synchronize within a couple of hours. Deploying contracts or making businesses needs test ether, which has no value and can be purchased free of any faucets. Testnets are public blockchains with several other users and tokens running online. Disadvantages. You cannot use real money on a testnet. It runs on test ether. Consequently, you cannot measure protection against actual advisories because nothing is at stake. There are other elements of a decentralized blockchain you can't possibly check on a testnet. For example, transaction fees are not a consideration on a testnet, though essential to submit transactions because gas is free. Furthermore, the testnets often don't encounter network congestion as does the public mainnet. Local blockchain simulation advantages and disadvantages. The best choice for many testing purposes is to launch a private blockchain of a single case. Ganache, formerly called Test RPC, is one of the most common simulations of local blockchain you can interact with without any other participants. This shares many of the public testnet's benefits and drawbacks, but it also has some variations. Advantages: no synchronization and almost no data on the disk. You mine the first block yourself. No need to acquire test ether. You reward yourself mining bonuses that you will use for testing. No other users, only you. No other contracts, just those that you install after you launch it. Disadvantages: no other users means it will not work the same as a public blockchain. There is no competition for transaction space or transaction sequencing. No miners other than you say that mining is more predictable. Thus, certain scenarios that occur on a public blockchain cannot be checked. Not having any other contracts means installing anything you want to check, including dependencies and contract libraries. Some public contracts and their addresses cannot be recreated to check such situations, e.g., the DOA contract. Running an Ethereum client. You can try to run a full node if you have the time and money, even just to learn more about the process. Within this section, we cover how Ethereum clients Parity and Geth can be downloaded, compiled, and used. That needs some experience with using the operating system's command line interface. Such clients are worth downloading if you want to run them as full nodes, as test node nodes, or as clients to a private local blockchain. Hardware requirements for a full node. You should ensure that you have a machine with sufficient resources to run Ethereum full node before we start. To store a full copy of the Ethereum blockchain, you'll need at least 80 gigabytes of disk space. Whether you want to run a complete node on the Ethereum testnet as well, you'll need at least 15 gigabytes more. It could take some time to download 80 gigabytes of blockchain data, so it is recommended that you operate on a fast internet connection. Synchronizing the blockchain from the Ethereum is very intensive input-output, I/O. A solid-state drive, SSD, is the best alternative. When you have a mechanical hard drive disk, HDD, you need to use at least 8 GB of RAM as your cache. Otherwise, you may discover that your machine is too sluggish to completely keep up and sync. Minimum specifications. CPU with 2+ cores. Minimum 80 GB free storage space. Minimum 4 GB of RAM with an SSD, 8 GB plus if you have an HDD. 8 megabits per second internet download service. These are the minimum requirements for synchronizing a complete but pruned copy of an Ethereum blockchain. The Parity codebase is lighter on resources at the time of writing, so if you're running with less hardware, you'll probably see better results using Parity. If you want to synchronize in a reasonable amount of time and store all of the programming tools, databases, clients, and blockchains that we are addressing in this book, you'll want a better machine. Recommended specifications. Fast CPU with 4+ cores, 16 GB plus RAM, fast SSD with at least 500 GB free space, 25+ megabits per second internet download service. It's hard to predict how quickly the size of a blockchain will increase and when more disk space is required, so it's minimum to check the latest size of the blockchain before you start synchronization. Note, the specifications for disk size listed here assume you are running a node with default settings, where the blockchain is pruned from old state data, unless you run a complete archival node instead, where all of the state is stored on the disk. It would possibly take more than 1 terabyte of disk space. Parity. Parity is a full-node implementation of the Ethereum client dApp browser. It was written in Rust, a programming language for systems, from ground up, in order to construct a modular, stable, and scalable Ethereum application. Parity is developed by UK-based company Parity Tech and is released under the free software license GPL v3. You may use the Rust package manager Cargo to install Parity, or download the GitHub source code. The package manager always downloads the source code, so the two choices don't vary much. The first synchronization of Ethereum-based blockchains. Normally, when synchronizing an Ethereum blockchain, the customer must download and validate every blockchain and every transaction from the very beginning, i.e., from the block of origin. Although this way it is possible to completely synchronize the blockchain, the sync will take a long time and have high resource requirements. It will need a lot of RAM, so it will take a very long time if you don't have quick storage. Most blockchains based in Ethereum had been the victim of denial of service attacks at the end of 2016. When performing a complete update, the effective blockchains would begin to merge gradually. On Ethereum, for example, a new client can advance rapidly until it hits blocks 2,283,397. This block was mined on September 18, 2016, and marks the start of the DOS attacks. From this block, 2,700,031 blocks, November 26, 2016, transaction validation is incredibly slow, memory intensive, and I/O intensive. That results in validation times of more than 1 minute per block. Ethereum introduced a series of updates to fix the underlying vulnerabilities exploited in the DOS attacks using hard forks. By eliminating some 20 million empty accounts created by spam transactions, these upgrades have cleaned up the blockchain. When you synchronize with complete validation, the client may slow down and it can take several days or even longer to validate the blocks affected by the DOS attacks. Luckily, most Ethereum customers have an option to conduct a quick synchronization that skips full transaction validation before it synchronizes to the tip of the blockchain and then resumes full validation. For Geth, the quick synchronization option is usually called fast. You may need to link to your chosen Ethereum's chain's unique instructions. By example, Parity synchronizes easily. Note: only when beginning with an empty block database, Geth will operate fast synchronization. If you begin syncing without fast mode, you can't turn to Geth. Deleting the blockchain data directory is quicker and starting quick syncing from the start than continuing to synchronize with complete validation. Be careful when removing data from blockchain not to delete any wallets. Remote Ethereum clients. Remote clients deliver a subset of full client features. You don't hold the entire blockchain from Ethereum, so they're easier to set up and need much less data storage. Usually these clients have the ability to do one or more of the following things. Interacting with smart contracts, using payload info, browse the dApps and communicate with them, include connections to external infrastructure such as Explorer blocks, convert Ether units and get foreign exchange rates, inject Web3 instance as a JavaScript object into the web browser, using an instance of Web3 provided or injected by another client into the browser. Local or remote Ethereum node connection to RPC services. Some remote clients provide only basic wallet features, for example, mobile smartphone wallets. Full-blown dApp browsers are also remote clients. Remote clients typically provide some of the functions of a full-node Ethereum client without synchronizing a local replica of Ethereum blockchain by linking to a full node running elsewhere, e.g., by you locally on your computer or on your web server, or by a third party on your server. Let's look at some of the remote clients that are most common and the functions they provide. Mobile smartphone wallets. All mobile wallets are remote customers, since smartphones lack adequate resources to operate a complete Ethereum customer. Light clients are being created for Ethereum and not in general use. The light client is called experimental in the case of parity, and can be used by running parity with the light option. Popular mobile wallets include. We list these merely as examples. This is not an endorsement or a clue of the safety or functionality of these wallets. Jax, a multi-currency mobile wallet built on BIP39 mnemonic seeds, with support for Bitcoin, a variety of ERC20 tokens, Litecoin, Ethereum, Ethereum Classic, Zcash, and many other currencies. This is not an endorsement or any sign of the safety or functionality of these wallets. Jax is available as a mobile plug-in wallet on Android and iOS, and as a web wallet for a number of operating systems. Status, a mobile wallet and dApp browser with a variety of tokens and common dApp support. Registered for Android and iOS. Trust Wallet, a mobile Ethereum and Ethereum Classic wallet backed by the tokens ERC20 and ERC223. Trust Wallet comes from iOS and Android. Cypher Browser, a full-featured mobile dApp client and wallet enabled by Ethereum that allows integration with Ethereum apps and tokens, registered for Android and iOS. Browser wallets. Various wallets and dApp browsers are available as plugins or web browser plugins, such as Chrome and Firefox. There are remote clients running inside your browser. Metamask, Jax, Myetherwallet, MyCrypto, and Mist are some of the more common ones. Metamask. Metamask is a powerful browser-based wallet, RPC client, and basic contract explorer, introduced in the intro chapter. It's available on Brave browser, Chrome, Firefox, and Opera. Unlike other user wallets, Metamask injects a Web3 instance into the JavaScript window sense, functioning as an RPC client connecting to a variety of blockchains from Ethereum, Mainnet, Ropsten Testnet, Kovan Testnet, local RPC nodes, etc. The ability to insert a Web3 instance into external RPC resources and serve as a portal makes Metamask a very useful resource for developers and users alike. For example, it can be combined with Myetherwallet or MyCrypto, which acts as a Web3 provider and RPC gateway for those tools. Jax. Jax, introduced in the previous section as a mobile wallet, is now available as an add-on to Chrome and Firefox, and as a web wallet. Myetherwallet, Mew. Myetherwallet is a remote JavaScript browser-based application that offers a software wallet running in JavaScript, a link to common hardware wallets such as Trezor and Ledger, a Web3 interface that can unite to a Web3 instance inserted by another application, e.g. Metamask, a RPC client that can connect to a complete Ethereum client, a simple interface that can incorporate the client into an Ethereum framework. It should not be used as a primary wallet for applications, as it is exposed to threats via the browser environment and is not a stable key storage. Note: when accessing Myetherwallet and other browser-based JavaScript wallets, you need to be very alert as they are popular targets for phishing. Please use a bookmark to access the appropriate web URL and not a search engine or a link. MyCrypto. The Myetherwallet project divided into two competing implementations just prior to the publication of this book, managed by two separate development teams, a fork, as it is called in an open source growth. The two projects are renamed by Etherwallet and MyCrypto, the original branding. MyCrypto at the time of the split provided similar features as Myetherwallet, but the two projects are likely to diverge as the two development teams follow different goals and objectives. Mist. Mist was the first browser compliant with Ethereum, designed by the Ethereum Foundation. It includes a browser-based wallet, which was the first implementation of the ERC20 token standard. Also, Mist's key developer was Fabian Vogelsteller, author of ERC20. Mist was the first wallet to implement the camel case EIP55 checksum 2. Mist runs a full server and offers a complete dApp client with swarm-based storage and ENS address support. Conclusions. We discussed Ethereum clients in this chapter. Through replicating the blockchain on your own computer, you downloaded, enabled, and synchronized a node, being a participant in the Ethereum network and contributing to system safety and stability. And that's crazy. Alright, so I have the block right in front of my face. Conclusions. We discussed Ethereum clients in this chapter. Through replicating the blockchain on your own computer, you downloaded, enabled, and synchronized a node, being a participant in the Ethereum network and contributing to system safety and stability.